Audio Jungle. Audio Jungle.
Right. Now we'll talk about the free vertex flow. Free vertex flow. Or only vertex flow also you can say, but it will be self-understood things like if I'm saying vertex flow, that means it's a free vertex flow. Why? Because free vertex flow is what? Irrotational flow. It's a irrotational flow. So here we are able to write equation of potential function. If it is a rotational flow, then we are able to write potential function equation. All right. Now coming to the free vertex flow, then already we had proved for the free vertex flow, that is or vertex flow, that already we had seen the flow is what? Basically circulatory flow. Okay, that already we had seen in case of the vertex flow, where I had explained free vertex and force vertex. So that time I had explained vertex flow is nothing but circulatory flow. It's a circulatory flow. What is the mean of circulatory flow? That also I will prove, but here I can write circulatory flow means the all streamlines, streamlines are concentric circles. Okay, all, and this I will prove, don't worry. All stream lines are concentric circles. Concentric circles. This is very important. Now, if you also remember, I had given, because it's a circulatory flow, it's a circulatory flow, so only tangential velocity will exist. Na? So for the circulatory flow, it's very clear. If you write radial velocity, so radial velocity will be 0 and tangential velocity will not be 0. That is condition for the circulatory flow. Okay, so vertex flow, again I will write vertex flow is a circulatory flow. Circulatory flow. And for the circulatory flow, two types of velocity will have generally, which is nothing but radial velocity and other is tangential velocity. So always remember, for circulatory flow your radial velocity will be 0 and tangential velocity does not equal to 0, means it will have a finite value. Just opposite to the source, just opposite to the radial flow. In case of radial flow, we'll have a radial velocity but tangential velocity was 0. But here for the vertex flow, or this is also called circulatory flow, where all streamlines are are concentric circles. Okay, become circulatory flow. So there only will have a tangential velocity. Okay, so and this tangential velocity already I have proved in my previous lecture, where I had explained the angular velocity, circulation, vorticity. So in circulation chapter, I had explained our tangential velocity for the circulatory flow is nothing but v theta, and this v theta is nothing but circulation upon 2 pi r. This was proved. Circulation upon 2 pi r. This was already proved. Okay, circulation upon 2 pi r. This was proved. Already proved. Okay, is already proved in my previous lecture. If you check tangential velocity for the circulatory flow, it was circulation upon 2 pi r, where v theta, I will write again, v theta is equal to circulation upon 2 pi r, where this is nothing but circulation, unit is meter square per second, and r is the radial distance. Meaning is very clear. Suppose this is the, sorry, meaning is very clear. Suppose about the point we have a circulation, and the circulation is nothing but gamma. If this radial velocity is what r, then what is the v theta? What is v theta? I can write this circulation here. This is the circulation gamma. So what is the tangential velocity v theta? So it was proved in my previous lecture. It is circulation upon 2 pi r. All right, done. Now one by one we have to derive for the equation of stream function and equation of potential function. So we'll write here equation of, first equation of potential function. Equation of potential function. So first we are going to derive the equation of potential function, right? See, we know the polar form because radial velocity, radial distance we have, tangential velocity will have. So first we'll write the polar form of the potential function. So as we know, v theta, that is the tangential velocity, and it was given 1 by r dou phi by dou theta, if you remember. Okay, and if you also remember, radial velocity was dou phi by, but this radial velocity, you know, it's a 0. Why? Because for the vortex flow, this is the vortex flow. So for the vortex flow, always remember radial velocity is what? 0. Okay, so we have to concentrate only on tangential velocity. It's a 1 by r dou phi by dou theta. You also know v theta is nothing but circulation of upon 2 pi r. Just now you have proved 1 by r dou phi by dou theta, right? Dou phi by dou theta. So r cancel out. What you will get? You will get circulation upon 2 pi. R cancel out both sides, so it's nothing but uh, dou phi by dou theta, or you can write d phi is equal to circulation by 2 pi into d theta. We can write like this. Now what you will do, you just integrate both sides. So what you will get? Phi is equal to circulation upon 2 pi, and d theta integration is nothing but theta. So if you see, it's very clear here. So this is the potential function. First of all, you should know the equation and you need to remember this. Okay, for the vortex flow, directly this potential function value they can ask to you. Okay, this theta is what in radian, circulation upon 2 pi is nothing but constant. All right, so done. Now my point is, if you want to draw the pattern of the potential function, so yes, you can draw. How you can draw? Because phi, what you have here, phi is nothing but circulation upon 2 pi, which is nothing but constant, into theta, means phi is directly proportional to theta. If you are changing the value of theta, you will have a different value of phi. So see, this is the different value of phi, because we have a different value of theta. See, so don't show the arrow line because it's a equipotential line. So if you check what is the theta here, see, you are measuring theta in this way. So here this will be the phi, because theta is 0, hence this phi is nothing but 0. Okay, and here because theta is nothing but pi by 4, means 45 degrees. So your what it is called, pi value, that is circulation upon 2 pi into pi by 4. Pi cancel out, circulation upon 8, right? Similarly here, this is just say this is the phi 1, this is what phi 2, so here it is phi 3. What will be the phi 3? What is the theta here? So theta is pi by 2. So pi cancel out, you will have a circulation upon 4, right? Like this. So this is what equipotential line. These are the equipotential lines. Okay, these are equipotential lines. Equipotential lines. Done. But and but what about the equation of stream function? So equation of stream function for the vortex flow. So we can have equation of stream function. Equation of stream function, right? So what will be the equation of stream function here? See, it's very simple. You know very well that radial velocity here for the vortex flow will be 0 and tangential velocity is nothing but v theta, and for the stream function v theta is nothing but minus dou psi by dou r, if you remember. Okay, so because this is nothing but vortex flow, so for the vortex flow vr is 0, vortex flow radial velocity will be 0, and what is the v theta? We know very well, circulation upon 2 pi r, and this is minus dou psi by dou r, right? Minus dou psi by dou r, yes or no? Minus dou psi by dou r. Then write this. Now the point is, you can take this value, d psi is equal to what? You can write, d psi is equal to minus circulation upon 2 pi r into dr. So what you can write, d psi is equal to minus circulation upon 2 pi dr by r, like that you can write this. Now again you just integrate both sides, because this is constants, you can take outside. So here it is, circulation is equal to what will be the value? It's a circulation upon 2 pi, and dr by r is nothing but ln r, right? Ln r, already I have told you what this r value you can write. You can write minus circulation upon 2 pi ln r. R is nothing but x square plus y square in root. Like this you can write. So automatically, if you see the psi values, it's nothing but minus circulation upon 2 pi ln r, or that also you can write circulation upon 2 pi ln root of x square plus y square. What is the x square plus y square is equal to r square? That is equation of circle, right? It's a equation of circle. So because it's a vortex flow, so I can say this is the center point is the center of vortex, and if you see, stream function psi is directly proportional to radius r. If radius you are changing different stream function, you will be getting something like this. And it's a circulation, so, and it's a streamline, so you have to show the direction also. This is what, this is nothing but streamlines. So always remember, dear, it's a very important point here you got, that in case of the vortex flow, okay, in case of, this is note, in case of vortex flow, in case of, vortex flow streamlines are, streamlines are circle or concentric circle, meaning is same. are concentric circles. But in case of the equipotential lines, always remember equipotential lines are the radial lines. Equipotential lines are the radial lines that you need to remember. Okay. In case of the vortex flow, equipotential lines are radial lines. So hope this one is very clear. Again, you can merge both equipotential line and streamlines. If you want, you can merge it, no issue. But my point is that gate point of view or any one day exam, what you understood. See, uh, one side I can write radial flow, another side I can write vortex flow. If I say radial flow, so automatically it should come in your mind source flow as well as sink flow. Automatically it should come in your mind for the radial flow only VR velocity will exist and tangential velocity will be 0. But if it is vortex flow, then automatically it should come in your mind for the vortex flow only tangential velocity will exist but radial velocity will be 0, right? Okay, first point. Second point, in case of the radial flow or source or sink, all streamlines or all equipotential lines are circles. But in case of vortex flow, all streamlines are circles or concentric circle. Okay. In case of the third point, in case of the radial flow, all streamlines, all all streamlines are all streamlines radial flow, na? So all streamlines are radial lines. Third point, here all equipotential lines are radial lines.